Hi to everyone and welcome to this DFT Incorporated webinar. Okay, right now I'd like to introduce today's presenter, Arie Bregman. Arie is the Vice President and General Manager of DFT Incorporated. A 35-year industry veteran, Bregman is active in the U.S. Valve Manufacturers Association, serving on the group's education, training, and technical committees. He's also a member of the VMA Board of Directors. Bregman holds a Master of Science degree in Mechanical Engineering from Worcester Polytechnic Institute in Worcester, Mass. So, Arie, welcome to today's event. And with that, I'm going to pass things over to you to get us started. Arie, go right ahead.
Hello, my name is Arie Bregman. I'm Vice President and General Manager for DFT Inc., and we're located in Exton, Pennsylvania. I've been in the valve industry for over 40 years, involved in the design and manufacture of quarter-turn ball and butterfly valves, check valves, and linear and rotary operated control valves. DFT manufactures inline axial flow check valves, sometimes called nozzle-style check valves, as well as linear operated severe service control valves. And I'm going to be your webinar host for today, so welcome. So we struggled for a little while trying to come up with a name for this seminar. And what we wound up with is kind of we're putting ourselves in the viewpoint of the customer and asking the question, why are we always having problems with this valve in this location? Many times valve problems are not a function of the valve at all, but problems with the piping system, either the design, the valve location, maybe it's poor installation practices, or selecting the wrong valve for that particular application. Our goal today will be to help you understand how important it is to understand all the different factors that come into play to create a valve that can be problematic in a specific location, and yet work just fine in some other locations. So without postponing the inevitable, let's get on with the subject and let's explore and learn as we go. So these are the 7 topics that we're going to be covering today and get into some level of technical detail on each of these points. We're going to talk about general valve and piping design rules, and related to that, some common pipeline design mistakes that we see. We'll get into valve installation guidelines and then also some valve maintenance guidelines. We're going to talk about what is the best check valve for your application. We're going to then get into common myths and compare that to reality, and end all this with some important gasketing information that you really need to know. With these 7 subject areas, there is a lot to get into, but it makes the most sense, at least to me, to talk first about just some general design rules for piping and system design that will lay a good foundation for what we need to talk about next. And we'll probably set the stage for maybe some questions that'll pop up. And if you have those questions, please feel free to send them in. There is information contained in the webinar information up front that will give you the email address to send your questions to. If I don't get to those answering those questions during this webinar, I will absolutely follow up with you afterwards and send you an email and try to give you a good answer or clarification or whatever it is you're looking for on that particular question that you had. So what is the best location to place a valve in a piping system? It should be pretty straightforward, I guess, that all valves will work best when installed in a non-turbulent flow condition. But if it was all that obvious, then maybe I wouldn't even have to state that up front. But we recommend that you have 5 nominal pipe diameters, or 5 times the nominal pipe size of straight pipe, both upstream and downstream of the valve. We understand that this may not always be possible, and DFT has a very robust design for our products, which allows these valves to be installed in less straight pipe than that. But generally, all valves will work best when you have 5 times the nominal pipe size of straight pipe upstream, and at least 5, more is better, but at least 5 diameters of straight piping on the downstream side of the valve. So I called the last slide rule number 1, and that is the 5 diameters upstream and at least 5 diameters downstream of straight pipe to have a good location to install a valve. Rule number 2 is that properly sized check valves are essential for optimum system performance with minimum maintenance required. All check valves require pressure from the fluid velocity to open the valve and maintain a stable position. The minimum pressure required to open a check valve is called the cracking pressure, and you probably need 2 times that differential pressure to get the valve from its cracking pressure to its fully open position. So I said rule number 2 is properly sized check valves are essential. Well, what is the minimum flow rate that a check valve can handle? And the answer to that is that you really have to perform flow sizing calculations for check valves. It's every bit as important as doing the sizing calculations that you do for on-off or control valves within your system. And you have to keep in mind that it's the fluid pressure that opens the valve. There's no other actuator that's going to open or close the valve other than what's going through the pipeline. So if you can keep rule number 2 in mind at all times, you can save yourself a lot of headaches with check valves that just don't seem to work. So my last of the rules, which is rule number 3, and you can breathe a deep sigh of relief. There's only 3 rules to remember. Has to do with horizontal versus vertical pipelines, and does it really matter in terms of valve placement? And it really does. A horizontal line is always preferred because it takes gravity out of the equation. Many styles of check valves will work in horizontal pipelines, but only axial flow or sealant check valves work well when installed in vertical piping. And in vertical piping, you also have to consider, is flow going up or is flow going down? Because that really does make a difference in some of the force balance dynamics that are going on within the valve itself. So try to install the valves in horizontal lines, but when you can't, if it's a vertical line, the best valve for a vertical line is always going to be an axial flow or sealant check valve. So with those 3 rules in mind, let's move on to what I call piping design mistakes. And I'm going to put some quotations around that phrase. I'm not trying to be too forward with that, but we really are dealing with mistakes. We're trying to cram the valves into small, tight spaces, and it's just a mistake that if there's any way to avoid it, it should be avoided. In the upcoming slides, I'm going to give you some design rules that really follow commonly accepted good piping practices. So let's start with choosing our valve location wisely. And for that, we need to go back to rule number 1. The ideal location should be 5 diameters of straight pipe upstream and downstream of the valve. Valves that are too close to pumps, elbows, expansion joints, or even other valves can cause problems. All of these upstream of the valve will cause turbulence, which can lead to instability of the disc of the check valve, and that will in turn lead to wear and component failure in time. So always keep rule number 1 in mind that 5 diameters upstream, 5 diameters downstream is a good place to put the valve. It obviously means that you need 10 diameters total length minimum to put any valve, but that's basically true whether we're talking about check valves, ball valves, control valves, any kind of valve. It really needs a laminar flow situation to give you the optimum performance. The DFT axial flow check valve can be installed on the upstream side of isolating valves. If the isolating valve is throttling, clearance, as shown, should be allowed to ensure full pressure recovery after the check valve. And that's just to make sure that you don't have some turbulence coming through the check valve that's going to upset how the downstream isolating valve is then working in terms of its throttling capability. We do provide a very robust design, but even with that, valves create turbulence for other valves. And we need to keep rule number 1 in mind, that you need to have a little bit of length, a little bit of straight pipe in between valves to ensure that the flow can restore itself to a laminar situation. Flow conditions are very important, and you always need to do the sizing calculations. Just blindly assuming that you just matched the nominal valve size to the nominal pipe size and not performing any sizing calculations will cause you trouble in a lot of circumstances. Make sure that your flow conditions will be sufficient to fully open the valve under minimum flow, maximum flow, and normal flow conditions. This will ensure optimum valve performance with minimum valve maintenance. And for this, I'm going to ask you to go back and remember Rule 2, which says that properly sized check valves are essential for optimum system performance and minimum maintenance. Let's go back for a second and think about rule number 3, which was the vertical versus horizontal line selections. Installing swing check valves in vertical pipe runs is going to cause you a problem almost every single time. And that is, the reason for that is that you're dealing with gravity. The internals of the swing check valve will respond to gravity, and flow is going downwards in a swing check valve. It will always be open and not do its job. If you have vertical lines with flow going up, then of course you're dealing with another situation where gravity may cause the disc to slam against the seat, leading to potentially severe water hammer. Only axial flow check valves will perform well in vertical piping locations, but consideration has to be given to if the flow is going up or down in that vertical pipe run. So while we're talking about vertical versus horizontal lines, it kind of leads us into the subject of water hammer. And there are some simple solutions for water hammer that we want to discuss right now. In vertical piping, the easiest thing to do if you have water hammer is to replace the swing check or double door valve with an inline axial flow style check valve. The stronger spring of the axial flow check valve will ensure that the valve will close before the reverse flow happens, and that's very important. Closing the valve before flow reverses will eliminate most of the water hammer, and that's the real advantage of the axial flow style of check valve. You have to just keep that in mind, that the spring is helping to close that valve and is opposing the flow while it's going forward, but it's also allowing the valve to close during that forward flow so that we avoid the reversal of flow, which is going to lead to the water hammer situation. So we've talked about some guidelines for better piping designs and how to avoid some common mistakes that lead to valve problems. Let's talk about good installation practices next. Check valves that are installed in vertical pipelines, as I said before, are sized a bit differently for flow up versus flow down. And basically, that's because the spring has to be adjusted based on the effects of gravity. Flow going up can use a standard cracking pressure spring in most circumstances. However, flow that goes down may require a stronger spring than the standard spring to compensate for the weight of the disc, as well as any static head of the media that you're trying to keep above the disc. So keep that in mind, that flow down may require something a little different than the standard off-the-shelf axial flow check valve. And sort of on a related subject, it is possible that axial flow valves can have low cracking pressure springs, lower than the normal standard off-the-shelf variety. That can easily be accommodated up to a point. For instance, a 3-inch check valve with a 0.1 psi cracking pressure is very possible, but a 30-inch valve with a 0.1 psi cracking pressure may not be possible. It all relates to the physics and friction and everything that's going on dynamically within the check valve. But we can accommodate low cracking pressures and do that all the time, for instance, on condensate return lines where they're being gravity fed back to a condensate pump. Low cracking pressures are essential to good pump operation in those kinds of situations. So we're talking about installation of valves in a piping system. Let's talk about excessive use of pipe dope or thread sealant on screwed end type of check valves or a screwed end type of any kind of valve. The biggest enemy of any kind of valve is sloppy installation practices. As you can see in this picture, getting the pipe sealant, being a little too generous with it as you put the pieces together, may force some of that sealant to the internal features of the valve. And that's almost always, if not always, going to cause a seat leakage problem with that valve. The sealant material needs to be used but not overused in all situations. and you need to be careful that you don't push it inside the valve and gum up the disc or the spring, or if it's a ball valve, gumming up the ball and the seat and getting in there and causing all kinds of problems. So a little is good, a lot is bad. One problem that we see a lot is that valves may have to be removed from a piping application for whatever reason. If you put your wrench on the wrong half of that valve to unscrew it out of the line, you may actually wind up disassembling the valve as you do that by unscrewing the two halves of the valve. So it's important that when you need to remove a valve, a screwed-in type valve from a piping system, that you put the wrench on the appropriate end of the valve that's going to prevent it from unscrewing itself. The effect of doing that could result in a body seal leak because when you screw the two halves back together, and maybe you've only cracked the two apart slightly, you may pinch the body seal O-ring that's between the two halves. So please, please, please pay attention to the flow direction in the piping before you start installing the check valve. Make sure you put it in the right way the first time. And if you do have to take it out, put the wrench on the correct half that's going to not allow the two halves of the body to become disengaged from each other. So does the valve that I'm installing need to be in a perfectly level pipeline in a horizontal application? And there is kind of a yes and no response to this, but I'm going to say no. It doesn't matter, but it really does help. Swing checks and tilting disc check valves generally have a seating surface that's machined on about a 5-degree inclined plane relative to the valve center line. If your pipeline is at any angle greater than 5 degrees, that may cause the disc not to touch the seat and hence leak. Axial flow check valves don't experience this problem because there's an internal spring and it's going to keep the disc pressed against the seat. And so that's the no part of the answer, but the yes part pertains more to other styles of valves where there is no spring and gravity is your friend in trying to help seal the valve. So still on the subject of installation guidelines, my last thought is to take a final look. Clean out the lines before you're buttoning up the pipeline. It may seem obvious, but you'd be surprised what will get into the pipe during the construction process. There could be weld rod, wrenches, 2x4s, just about anything you can imagine, a lot of things you couldn't imagine. And it all damages the seating surfaces and delays startup. So always take a final look before that line gets closed up and make sure there's nothing in that line that should not be there. Okay, so let's move on a little bit and let's talk about valve maintenance guidelines. All right, so the first question might be, should I be using oils, greases, or lubricants when doing maintenance on my valves? And I guess the answer to that is a little bit of a cop-out, but it's always follow the manufacturer's recommendations. Read their maintenance instructions before you start. Some valves require these kinds of oils, greases, lubricants, and others do not. As a general rule, whenever possible, I would say do not use greases or lubricants because their presence may be detrimental to your process. So it's best to select valves that don't require these kinds of additives, if you will, to help their performance. Always go with a valve that can be used in a clean, dry, non-lubricated environment because it will save you a lot of headaches with your process later on. Always thoroughly clean the valve while you have it on your bench for maintenance. The cleaner it is, the better it will work. Greases and lubricants, loose rust or scale on the cast surfaces all need to be removed to ensure that the valve, when it gets installed, will work as good as it did when you rebuilt it and tested it on your bench. It's kind of corny to say it, but it's so true. Cleanliness is next to godliness in this kind of situation. A clean valve will never cause you a headache during startup. I know I said it just a few minutes ago, but I'll say it again. Always get the maintenance instructions for the valve you're working on. Even if you've been rebuilding valves for 30 years, the manufacturer may have some special requirements that you really need to know about. It's better to do the repair right the first time than to have to do it all over again, and I think nobody's going to argue with that sentiment. So always make sure you get the operating instructions or the installation instructions for the valve before you crack it open and start working on it. All right, so let's move away from valve maintenance for a while, and let's think about how to choose the best check valves for your application needs. A lot will go into choosing the right valve for that given application, and so I'd like to review some of the choices that go into picking the right valve. Okay, location factors. I did say this earlier on in this webinar, and I will say it again. Think back to rule number 1 and rule number 3. Trying to find the optimum locations in the system for your valves and where they're going to be installed is very important. Squeezing them in somewhere is only going to come back and haunt you. Sizing of check valves is so important. I just find myself feeling like I'm overemphasizing it, but in reality, I never can. You have to remember that check valves that you specify and install are only going to be opened by the media that flows through the valve. So considering the min flow, max flow, and normal flow conditions is absolutely essential. If you need help with this process, DFT is there to help you with that. To get the sizing right, we can provide travel stops to conform to your exact flow conditions. Don't just specify the valve size by the line size. You need to do the math and get it right, because it will have its payoff in increased system reliability and decreased maintenance of the valves that are in that system. So we're talking about choosing the right valve for the application that you have. And naturally, we have to talk about valve materials. Generally, the valve body material will match the pipe and flange material. So a carbon steel line will demand a carbon steel valve body. And that's really the most common in many applications. Probably a close second would be cast iron. And right after that would be a stainless steel materials. But it seems to me that, at least 2/3 or 3/4 of the time, you're going to be dealing with a carbon steel body material. And there are many choices within this family that are based on external environment as well as process temperatures. So carbon steel is not carbon steel. There's ones that are more suitable for lower temperatures, as well as ones that are more suitable for high temperatures. Trim materials are usually selected to be more corrosion resistant than the body. Hard facing is another option that can be selected when there is a more of an erosive concern. For instance, there may be solids in the media stream, and you want to prevent those solids from eroding the sealing surfaces of the valve itself. So as I said, the solids in the media may cause pitting or erosion on critical sealing surfaces of the valve. But there are fines and there are solids, and there's a big difference between the two. You should check the maximum size of any solids against the manufacturer's maximum size recommendations. A 1-inch diameter solid may travel very easily down a 4-inch diameter pipeline, but it may not pass through the 4-inch valve. So consult the manufacturer and make sure that what's going through your pipeline will also go through the valve. Okay, so we've given a lot of thought to choosing the right valve for the right application. Now let's spend a little time dispelling some of the myths that surround the selection of valves and dispel some of those notions. And so let's talk about a few of those right now. So here's 2 very common myths about stainless steel. One is that stainless steel does not rust, and the other is that stainless steel is not magnetic. And both of those are false assumptions or false myths that need dispelling. First is that rust on stainless steel is caused by free elemental iron that's resident on the casting surface, and it's particularly true with castings, whether they're whatever process they might be made by. There are a lot of different processes that are involved within the foundry itself, including shot blasting to clean and grinding, and they all leave free iron on the surface, which will eventually cause rust to appear. The solution is to pickle or passivate the casting, and that will remove the iron residue. The other myth is that stainless steel is not magnetic, and that's absolutely not true. Cast stainless steel will also be very weakly magnetic due to the ferrite content of the microstructure of the cast material. And that's not true with a wrought material or a forging, but is absolutely true of a cast material. And both 300 and 400 series stainless steels will be somewhat magnetic, and you can put a magnet against it and you can feel the attraction of the magnet to the valve body. And it's not just the free iron on the surface, it's also the ferrite that's part of the microstructure of the casting. Another myth to be dispelled is that higher CV is always better. And this goes back to rule number 2. When check valves are being selected, sizing the valve is absolutely important, and sizing the valve properly for the flow condition is of utmost importance. The rules that you apply for sizing on-off valves do not apply to check valves. When you have a on-off valve, you calculate a desired CV, and you select a valve with a higher CV for that particular application. With check valves, you calculate your desired CV, and then you choose a check valve that has a slightly smaller C sub V, which is the valve coefficient, and it's expressed in gallons per minute at 1 psi pressure drop. But you really need to apply the rules specifically for check valves, and that is selecting a valve with a CV slightly lower than your calculated CV. So let's put aside the myths versus reality and set Merlin and the unicorn aside for a little while. And let's talk about gasketing and gasket information that's important to know. The gaskets in the piping system are as important as the valves themselves. And choosing the right materials and then installing them correctly is extremely important. With all the focus on fugitive emissions that we deal with, the gaskets have to be considered as well as any stem packings. And I'm going to talk about important gasketing information that you need to know in the upcoming slides. Gaskets are chosen to be compatible with the temperature, the chemical composition of the media, as well as the pressure of the system. And to prevent leaks or fugitive emissions from the gasket joint, it's absolutely necessary to follow proper tightening procedures, as well as proper torquing steps and sequences in tightening down the gasketed joint. One reason that we have gasketing problems is because it takes time to properly install a gasket. There are a few minimum required steps. There's pre-tightening. There's a 3-star pattern of tightening that as a sequence needs to be followed. And then finally, 3 rotational passes after having done the 3-star pattern tightening sequences. All need to be done. Many times we find that installers are just unwilling to take the time that is required. But the proper method has a few very important steps that cannot be overlooked or skipped. The first step I call pre-tightening. And first you need to inspect and clean all the bolts and threads and nut-bearing surfaces and lubricate them completely. And that means the bolt threads, the nut faces, and the washer faces. It's all very important. But the pre-tightening step is probably the most important because it stabilizes the flanges and keeps them parallel. So hand tighten all the nuts, and if possible, snug the nuts with a hand wrench. Again, this will stabilize the flange, keep everything parallel, and just give you a good starting point for a good, sound, tight gasket. After the pre-tightening step, the flanges are stabilized and parallel. The next thing we need to do is perform 3 star pattern tightening sequences. This is where everyone else starts with their procedures. And this is also why our pre-tightening step is so important. If you've ever replaced a head gasket on a car or even tightened the lug nuts when changing a tire, you know that there is a right way and a wrong way to tighten the nuts. In the star pattern tightening sequences, we give the bolts numbers so that we don't lose our place, and that's very important. There could be 8, 12, 16, there could be quite a number of them. So let's number them all so that we don't lose where we're starting. And we always start each sequence with the number 1 bolt. Doesn't matter which one it is, call it number 1. Go around in a star pattern and go 1, 2, 3, 4 all the way around the pattern. You can identify this with a marker pen or whatever sort of marker you prefer. But follow the star pattern tightening sequences based upon the number of bolts for each of the 3 rounds, progressively increasing the torque, starting at 30%, then going to 60% of max, and then finally the full 100% torque value. The graph that you are looking at illustrates the bolt stress for each bolt after we have completed the 3 sequential tightening rounds. You can see that the stresses on the bolts are not quite equal, and they vary by 20 to 25%. And they are also not within the desired bolt stress range as indicated by the 2 red lines for upper and lower limits. In order to make the bolt stresses more uniform, there is one more step that's required, and it's very important. The final sequence is the rotational tightening. And we start at the number 1 bolt, and we continue with the 100% final torque value. In this last step, the goal is to keep the wrench setting at that full torque setting, and this time tighten in a clockwise rotational pattern, starting with number 1. We recommend that you go around 3 full times, and this will bring the loads of the bolts into kind of an equilibrium status. Optionally, you could also and should also consider retorquing after between 4 and 24 hours to compensate for any gasket creep that may have occurred, which will relax the stress in the bolts. As you can see in this graph, the load on the fasteners are now well within the range of acceptability between the high and the low limit, and the stress is much more uniform as well. The point we're trying to get to is that when we get a consistent load on the fasteners going around the flange, we are also getting consistent, even compression on the gasket as well. You've created a series of springs around the flange. They look like bolts, but they act like springs. And the bolts are stretched uniformly around the flange, and all that they want to do is go back to their original shape. And this is what is known as the clamping force that holds everything together. So it's so important to go around those extra 3 times in a clockwise manner and just keep everything snug. And as I said, as an option, you can even consider going back 24 to 48 hours later and rechecking all the torques to compensate for any gasket creep that might have occurred. By using good installation practices, you achieve an increased gasket contact area as well as a uniform gasket compression. But most importantly, you've increased the life of the gasket. Secondarily, you will also reduce leakage, which of course means reduced maintenance. All that leads to more productivity for your plant, which means your workplace is more productive, more environmentally compliant. And as we all know, in these times, environmental compliance, reducing fugitive emissions is extremely important. Well, we've covered a lot in this webinar, and I hope it's been interesting to you. We've talked about general design rules. We've talked about common piping design mistakes. We've discussed some solutions for water hammer as well as valve installation guidelines and valve maintenance guidelines. Choosing the right valve for the right application. We've dispelled some myths and compared them to reality. And finally, we've covered some gasketing issues. All of this I hope you found very important.
Okay, Arie, thank you very much for that great presentation. And we do have some questions that have come in from the attendees. Okay, Arie, here's your first question. I have to put the check valve right after the pump. I have no other options. What do I do?
Okay, that's a very good question. You have to consider the impact that the turbulence from the pump outlet will have. You need to really select the most rugged design that you can find to install in that particular location. So consider a dual-guided axial flow design valve and size the valve for the flow conditions at the pump outlet. Restricting the valve's opening travel will be necessary if the flow conditions do not open the valve fully. The disc has to travel to a hard stop, otherwise the disc will be chattering and will eventually fail because of increased wear of the valve in that area.
Okay, Arie, thank you very much for that answer. Here's another question. You explained about vertical lines with flow going up versus flow going down and the differences in spring cracking pressures for axial flow checks. Could you please clarify?
Okay, well, if flow is going up, then gravity and the weight of the disc will help close the valve. But the spring in the valve will ensure that the valve closes before the flow reverses, and this is the key to reducing and eliminating water hammer. If the flow is downwards, then gravity and the weight of the disc are working against you. Now the spring has to be changed to compensate for the weight of the disc, which means a stiffer spring. So it's, I think, as simple as that. Just remembering the effects of gravity and thinking about the balance of forces acting on that disc, whether they're the weight of the fluid, the forces associated with the velocity of the fluid flow, but most importantly, don't forget gravity.
Okay, Arie, thanks again for that answer. Here's your next question. I'm not clear on how an axial flow check valve can reduce or eliminate water hammer. Can you please clarify that statement?
Okay, also a very good question. Water hammer occurs when the flow has reversed its direction and comes crashing into what is now a closed valve. The spring that's inside the axial flow style check valve is always opposing the flow, and as the flow starts to reduce, the spring will start to close the disc. If you have a half psi cracking pressure valve, the flow that corresponds to that pressure across the disc will be overcome by the spring at a flow that's equal to a differential pressure of 1/2 psi. The spring will close the valve against forward flow and thereby eliminate the reversing flow and thus the water hammer.
Okay, Arie, thanks for that answer. We've got time for another question. Let's take a look. Axial flow check valves are a lot more expensive than a swing style or double door style. How do I justify the additional cost?
Well, yes, it's true. The slightly higher cost of the axial flow style valve is a fact of life, but it is more than paid for with reduced maintenance costs and higher system uptime. Oftentimes, the downtime for a process can be expressed in tens of thousands of dollars per hour. Less maintenance means less cost, but it also means more process uptime, which means more revenue. So just do the math, and you can justify a more expensive or slightly more expensive, but a better valve for that application. You'll come out the winner every time.
All right, Arie, we're going to have to wrap things up right there. Arie Bregman, thanks so much for taking the time to be here with all of us today. And thanks to all of our audience members for being part of this webinar event. Take care and have yourselves a great day.